Look up at the night sky, and you'll see more than just stars. You'll witness galaxies, those vast, swirling tapestries of light. Each one a masterpiece sculpted by forces we're only beginning to understand. What if I told you that hidden beneath their breathtaking beauty lies a cosmic battle, an invisible dance of energy and matter shaping everything from the smallest star to the largest supercluster? These aren't just random formations, they're the fingerprints of the universe's most powerful and mysterious influences. For centuries, we've gazed at these celestial wonders, but now science is peeling back the layers to reveal something even more astonishing: the hidden hands that mold the cosmos itself. Imagine standing at the edge of a galaxy, watching as gravity twists gas into spirals, dark matter weaves unseen scaffolds, and magnetic fields stretch across light years like invisible threads. These are the cosmic forces, the architects of the universe, and their secrets are locked within 32 groundbreaking theories that could rewrite everything we know about how galaxies are born, live, and die. Some of these ideas will shatter long-held beliefs. Others will open doors to realms we've never dared to explore. What if black holes aren't just destroyers but creators? Could dark energy be painting the universe on a canvas we can't even see? The answers lie ahead, and they'll challenge you to rethink your place in the cosmos. This isn't just a story about distant stars, it's a journey into the heart of existence itself. Every galaxy holds clues, and every theory we uncover brings us closer to solving the ultimate puzzle: how the universe sculpts its grandest structures. From the violent births of quasars to the delicate balance of cosmic webs, the forces at work are more extraordinary than fiction. So let's dive into the mystery together. By the end of this exploration, you won't just see galaxies as static pictures in a telescope, you'll feel the pulse of the forces that shape them. And maybe, just maybe, you'll glimpse the universe not as a stranger, but as a storyteller whispering its secrets across the void. Galaxies aren't just scattered across the cosmos at random. They're like pages in a grand cosmic diary, each one etched with the history of forces we can't see, but whose influence is written in starlight. Picture a spiral galaxy, its arms swirling like cream stirred into coffee, and you're witnessing gravity's masterpiece. But look closer and something doesn't add up. Those outer stars should be moving slower, yet they race around as if tugged by an invisible leash. That's where dark matter enters the story, an enigmatic presence weaving through space, holding galaxies together with its gravitational grip. It's the universe's hidden scaffolding, accounting for nearly 85% of all matter, yet refusing to reveal itself directly. Then there are elliptical galaxies, smooth and featureless as pebbles, their stars orbiting in chaotic directions. These aren't gentle cosmic relics, they're the survivors of violent mergers, where colossal collisions stripped away their spiral arms and left behind this ghostly symmetry. And what about irregular galaxies, those cosmic misfits with no defined shape? They're the rebels of the universe, often caught in gravitational tug of wars or blasted by bursts of star-forming energy. Every shape, every structure is a clue, a reaction to the forces that have shaped it over billions of years. But here's the twist: galaxies don't evolve in isolation. They're part of an intricate web connected by filaments of dark matter and gas, trading material like cosmic marketplaces. Some feast on smaller neighbors, growing fat with stolen stars, while others are stripped bare by larger predators. And threading through it all are magnetic fields, invisible rivers of energy that guide the flow of gas and dust, shaping where stars can form. It's a dynamic, ever-changing playground where the rules are written in gravity, dark matter and energy, forces so powerful they can sculpt an entire galaxy, yet so subtle we're only now learning to read their signatures. The first theory we'll explore peels back the curtain on dark matter's role, suggesting it's not just a passive backdrop but an active sculptor. Could it be that these invisible particles don't just hold galaxies together but dictate their very forms? The answer might lie in the way dark matter clumps and flows, creating gravitational wells where gas pools and stars ignite. One thing's certain: to understand galaxies, we must first decipher the silent language of the unseen. Dark matter doesn't just lurk in the shadows of the cosmos. It builds the very stages where galaxies perform their celestial dance. Picture this: an invisible ocean of particles, 5 times more abundant than ordinary matter, its gravity carving out vast wells in the fabric of space. These are the dark matter halos, colossal structures spanning hundreds of thousands of light years, and they're the reason galaxies have homes at all. Without their gravitational embrace, gas would never coalesce, stars wouldn't ignite, and those majestic spiral arms we admire would simply unravel into chaos. Recent supercomputer simulations reveal something extraordinary. When dark matter first clumped together in the early universe, it didn't just form vague clouds, it created intricate cosmic webs with filaments intersecting like threads in a spider's silk. Gas streams followed these hidden pathways, pooling at the intersections where galaxies would eventually bloom. It's as if the universe sketched its blueprints in invisible ink, and dark matter was the artist. Take the Milky Way. Our galaxy spins within a halo so massive it dwarfs all visible stars, yet we'd never know it was there without the way it tugs on everything around it. But here's where the mystery deepens. Some tiny galaxies, like those orbiting Andromeda, move in bizarrely synchronized planes like dancers, following a choreography that standard dark matter models can't explain. Even more puzzling are galaxies like NGC 1052, where stars seem almost untethered from their dark matter anchors. These outliers whisper that we might be missing a crucial page in the dark matter playbook. Could there be different types of dark matter particles interacting in ways we haven't imagined? Or is gravity itself behaving differently on cosmic scales? The plot thickens when dark energy joins the scene. While dark matter pulls galaxies together, dark energy pushes the universe apart, a yin and yang of cosmic construction and destruction. Next, we'll see how this relentless expansion force doesn't just stretch space. It sculpts galaxies by controlling which structures get to grow and which are doomed to fade into the void. Because in this grand cosmic theater, the invisible architects are always competing, and their battle leaves fingerprints on every galaxy we observe. While dark matter pulls the cosmos together, dark energy does the opposite. It's the universe's silent repulsive force, pushing everything apart at an ever-increasing speed. Picture a balloon expanding not just steadily but faster with each passing moment. That's the effect of dark energy, and it's rewriting the fate of every galaxy in existence. Discovered in the late 1990s when astronomers noticed distant supernovae were fainter than expected, this mysterious energy makes up 68% of the universe's total content. But its influence goes far beyond simply stretching space. It's actively shaping the architecture of galaxies themselves. Take cosmic voids, those vast, empty regions spanning hundreds of millions of light years. They're not just accidents. Dark energy's relentless push amplifies them, isolating galaxy clusters like islands in an ever-widening sea. As the voids grow, galaxies on the edges are pulled into filamentary structures, their gas supplies stretched thin, starving them of the fuel needed to form new stars. Over time, this could turn vibrant spiral galaxies into dim, aging ellipticals, their stellar nurseries shut down by the universe's expansion. But here's the real puzzle. Could dark energy's influence reach even further, warping individual galaxies from within? Some simulations suggest that in regions where dark energy dominates early, it might subtly alter a galaxy's internal dynamics, affecting how stars orbit or how gas collapses. Imagine a galaxy where the outer stars drift away faster than expected, not just from dark matter's grip weakening, but from space itself stretching beneath them. It's a controversial idea, but one that could explain why some galaxies look older or more diffuse than their environments suggest. The stakes couldn't be higher. If dark energy continues accelerating, distant galaxies will one day vanish beyond an invisible horizon, their light never reaching us again. Meanwhile, closer galaxies may find themselves trapped in a solitary fate, cut off from cosmic neighbors as the space between them becomes unbridgeable. Yet amid this grand cosmic tug-of-war, another force operates on a finer scale, one that sculpts galaxies not with gravity or expansion, but with invisible magnetic fields weaving through the void. Magnetic fields might be the universe's best-kept secret, so faint you'd never notice them, yet they stretch across entire galaxies like cosmic puppet strings, quietly directing the show. Imagine a spider's web, invisible to the naked eye, but strong enough to guide the motion of everything that brushes against it. That's the power of galactic magnetism. These fields are 1,000,000 times weaker than Earth's, yet they shape the birthplaces of stars, steer colossal gas clouds, and even leave their fingerprints in the light we observe. Take a spiral galaxy's arms where newborn stars blaze to life. Astronomers studying polarized light that vibrates in a specific direction have mapped magnetic fields threading through these regions like grooves on a vinyl record. The fields align with the spiral arms as if tracing the galaxy's skeleton. In places like the Whirlpool Galaxy, these invisible lines act like cosmic highways, channeling gas into dense pockets where gravity takes over, collapsing it into stars. Without magnetism's subtle guidance, star formation might be chaotic, sporadic, or even stifled entirely. But here's the debate. Are magnetic fields just background players, or do they hold real sculpting power? Some argue they're too weak to compete with gravity's dominance. Yet in galaxies like M82, where frenetic star birth creates supersonic winds, magnetism appears to corral those eruptions, preventing them from tearing the galaxy apart. And in the vast voids between stars, magnetic fields might help gas maintain its structure, like an invisible scaffold keeping clouds from dissipating into nothingness. The real twist comes when we consider how these fields originated. Were they forged in the early universe, amplified by the motions of ionized gas over eons? Or do supermassive black holes, those monstrous engines at galactic centers, inject fresh magnetic energy into their surroundings, like invisible conductors orchestrating a symphony? Speaking of black holes, their role in galaxy evolution isn't just destructive, it's paradoxically creative. Next, we'll explore how these gravitational behemoths don't just devour matter, they can ignite it, shaping galaxies from the inside out with eruptions powerful enough to redefine an entire cosmic neighborhood. Supermassive black holes aren't just lurking in galactic centers, they're active conductors, orchestrating the rise and fall of stars with bursts of energy so powerful they can reshape entire galaxies. Picture a sleeping giant suddenly awakening, devouring nearby gas until it can't swallow another bite, then belching out jets of plasma at nearly the speed of light. These aren't just cosmic tantrums, they're part of a delicate feedback loop, a self-regulating system where the black hole's appetite determines its galaxy's future. Take the quasar 3C273, a brilliant beacon 9 billion light-years away. Its jets stretch over thousands of light-years, heating surrounding gas to millions of degrees, rendering it too hot to collapse into new stars. This is black hole feedback in action. Too much activity, and star formation shuts down like a furnace starved of fuel. Entire galaxies can become red and dead, their stellar birthplaces sterilized by these eruptions. The same process might explain why massive ellipticals packed with ancient stars often host the most voracious black holes. But here's the twist: black holes aren't just destroyers. In galaxies like Centaurus A, their jets plow through gas clouds, compressing them into dense knots where gravity takes over, sparking bursts of new star formation. It's as if the black hole's fury carves out niches where creation can thrive. Some theories even suggest these feedback loops could explain why galaxies tend to scale so precisely. The more stars a galaxy forms, the more material feeds its black hole, which then flares up to prevent runaway growth. A cosmic thermostat fine-tuned over billions of years, yet for all their power, black holes don't act alone. Their influence intertwines with another galactic sculptor, violent collisions where galaxies don't just grow, they merge, warp, and sometimes shatter entirely. Imagine two spiral galaxies, each with its own black hole, slamming together in a gravitational ballet that reshapes everything in its path. The aftermath isn't chaos but transformation, a rebirth where new structures emerge from the wreckage. And in that chaos, black holes may find their ultimate partners, spiraling toward each other until they too collide, sending ripples through space-time itself. Galaxies aren't always born, sometimes they're made, forged in the violent embrace of collisions so massive they rewrite the cosmic landscape. Picture a vast, serene spiral galaxy, its arms glittering with stars, unaware that a smaller neighbor is drifting inexorably toward it, doomed to be torn apart by gravitational tides. This is galactic cannibalism, the process by which larger galaxies consume smaller ones, growing fat on stolen stars and gas. The Milky Way itself is no stranger to this brutality. Studies of its halo reveal streams of stars, ghostly remnants of dwarf galaxies it shredded and absorbed over billions of years. Andromeda, our nearest galactic neighbor, is headed straight for us, set to collide with the Milky Way in about 4 billion years. When that happens, the two spirals won't simply crash, they'll entwine in a slow, gravitational dance, their stars flung into chaotic new orbits as their central black holes spiral toward each other. The result, a single, massive elliptical galaxy, its stars no longer arranged in delicate spirals but scattered in a shapeless swarm. This isn't destruction, it's transformation. But mergers do more than reshape stars. They scramble dark matter halos, redistributing the invisible scaffolding that holds galaxies together. Simulations show that when galaxies collide, their dark matter doesn't just blend smoothly. It clumps and stretches, creating ripples that can trigger new waves of star formation or leave behind vast star-poor regions. Some elliptical galaxies, those smooth, featureless giants, might owe their existence to multiple mergers, their original structures erased by repeated violence. Yet here's the haunting question: is every galaxy a product of such chaos? Some dwarf galaxies, like those orbiting the Milky Way, appear surprisingly pristine, their stars telling stories of quiet, isolated lives. Others, like the ultra-diffuse galaxies floating in cosmic voids, seem too fragile to have survived any mergers at all. The truth likely lies somewhere in between, a universe where some galaxies grow by devouring others, while some escape untouched, relics of a gentler past. But mergers aren't the only force reshaping galaxies. Between these colossal encounters, subtler sculptors are at work: cosmic winds, vast streams of gas blown outward by supernova or black hole jets. These winds can strip galaxies of their star-forming fuel or seed distant regions with the raw materials for new stars. Like invisible hands, they shape galaxies not through collision, but through erosion and renewal, a delicate counterpoint to the violence of mergers. And in that balance between destruction and creation lies the secret of how galaxies evolve. Galactic winds aren't just breezes, they're million-degree hurricanes screaming through space at thousands of kilometers per second, capable of stripping entire galaxies of their star-making potential. Imagine a newborn star cluster exploding in unison, its supernova detonating like cosmic grenades, blasting surrounding gas into intergalactic space. These aren't temporary disruptions, they're eviction notices for star-forming material, pushing galaxies toward premature aging. Hubble's keen eye has captured this drama in stunning detail, like in Galaxy M82, where supernova-driven winds create a glowing haze of ejected material stretching over 20,000 light-years, a visible testament to the violence reshaping its future. Yet not all expelled gas is lost forever. Some galaxies host cosmic fountains, where ejected material arcs back like water in a gravity-defying splash. Picture gas heated by stellar explosions, shooting upward until it cools and condenses, raining back down in shimmering filaments observable in ultraviolet light. NGC 25-3, a starburst galaxy 7 million light-years away, showcases this perfect recycling system, its outflows eventually returning to feed new generations of stars. This delicate balance between loss and renewal might explain why some galaxies keep forming stars for billions of years while others burn out young. The difference between winds and fountains often comes down to gravity's grip. In massive galaxies, supernova might lack the power to fully escape, creating fountains. But in smaller galaxies like the Large Magellanic Cloud, winds can punch through weak gravity, carrying away precious star fuel forever. Even black holes contribute. Their jets can carve bubbles in surrounding gas, lifting it away like steam from a boiling pot. The consequences are profound. Galaxies that lose too much gas become cosmic deserts, their stellar nurseries shuttered. What controls whether gas escapes or returns? Magnetic fields may act like invisible nets, trapping some material while letting other streams slip away. Dark matter halos play a role too. Their gravity can pull back wayward gas, turning potential winds into fountains. The interplay is so precise that astronomers now study these outflows to predict a galaxy's lifespan. One thing's certain, while mergers and black holes reshape galaxies dramatically, winds and fountains work in subtler strokes, like invisible sculptors chiseling away over eons. But these forces don't operate in isolation. Just as rivers flow into oceans, galactic winds eventually join something far larger, the cosmic web, a network of gas filaments connecting all galaxies in the universe. Within this vast architecture, even ejected material finds new purpose, feeding distant galaxies or pooling in intergalactic nurseries where future structures will rise. The next chapter in our cosmic story reveals how this web doesn't just connect galaxies, it births them. The cosmic web isn't just a backdrop, it's the universe's grand highway system, with galaxies strung along its filaments like pearls on invisible strings. Picture a colossal river network, but instead of water, these channels flow with dark matter and gas, funneling raw material into the gravitational basins where galaxies feast. Simulations like the Illustris TNG project reveal this in stunning detail. Gas streams along these filaments at hundreds of kilometers per second, crashing into galactic hubs where it ignites into stars. The Milky Way didn't form in isolation, it grew at the intersection of these cosmic currents, fed by tributaries of hydrogen that have sustained it for billions of years. But here's the cosmic irony. These same filaments that nourish galaxies can also trap them. In dense clusters like the Coma cluster, galaxies orbit at blistering speeds, stripped of their gas by the very web that birthed them. It's like a tree rooted in fertile soil, only to have its branches pruned by the wind. Some astronomers argue the web is a nurturing scaffold, guiding growth by concentrating resources. Others see it as a cage where galaxies in crowded nodes are doomed to starve as their gas reserves are torn away by violent encounters or heated to oblivion by intergalactic plasma. The debate hinges on location. Isolated galaxies along filament spines like NGC 4565 enjoy a steady supply of gas, their star formation humming along undisturbed. But galaxies plunged into crowded nodes, such as those in the Virgo cluster, often become red and dead, their gas stolen by relentless gravitational tides. The web giveth, and the web taketh away, a delicate balance between abundance and scarcity written in the language of gravity and motion. Now add neutrinos to the mix, those ghostly particles that stream through the cosmos almost untouched. Once thought too lightweight to matter, new simulations suggest they might subtly warp the cosmic web's structure. Billions of neutrinos, remnants of the universe's fiery birth, could be pooling in gravitational wells, altering how filaments bend and twist. It's a whisper of influence, but in a cosmos built on subtle forces, even the faintest players might hold unexpected power. The question isn't just how galaxies form, it's how the universe's most elusive particles might be quietly shaping the paths they follow. Neutrinos are the universe's ultimate ghosts. Billions pass through your body every second, leaving no trace, their presence detectable only by the most sophisticated instruments. These nearly massless particles, born in the hearts of stars and violent cosmic explosions, were long dismissed as too lightweight to shape galaxies. But new research suggests they might be quietly stirring the cosmic pot, their collective gravity subtly bending the paths of galaxies and dark matter alike. Picture a swarm of fireflies in a darkened stadium. Individually, their light is imperceptible, but together they cast a faint glow that shifts the entire room's ambience. That's the potential power of neutrinos on a galactic scale. Experiments like the South Pole's Ice Cube Neutrino Observatory have begun mapping these elusive particles, revealing how they cluster around massive structures like galaxy superclusters. Supercomputer simulations now show that while a single neutrino's gravity is negligible, their sheer numbers outnumbering atoms in the universe by 1 billion to 1 could warp space-time on vast scales. Some astronomers propose this might explain why certain dwarf galaxies seem to lack expected dark matter halos. Perhaps neutrinos' diffuse gravity is masquerading as part of the missing mass. Others argue their influence is more disruptive. Like cosmic static, their high speeds might prevent gas from collapsing into galaxies in the universe's sparsest regions. The debate hinges on neutrino mass. If these particles are even slightly heavier than current estimates, their gravitational footprint grows exponentially. Recent data from Japan's T2K experiment hints at this possibility, showing neutrinos oscillating between types in ways that suggest unexpected mass properties. If confirmed, it would mean these phantom particles aren't just passive observers, they're active participants in shaping the cosmic web, their gravity subtly sculpting where galaxies can form and how they cluster. Yet neutrinos are just one piece of an even deeper puzzle. To understand how galaxies emerged from the primordial void, we must rewind further, to the universe's first moments, when quantum fluctuations smaller than atoms laid the blueprint for everything we see today. These microscopic ripples, stretched to cosmic proportions by inflation, became the seeds of galaxies. The connection between quantum physics and galactic majesty isn't just theoretical. It's written in the very fabric of the cosmos, waiting to be decoded. To understand how galaxies emerged from the void, we must shrink our perspective way down to the quantum realm, where particles flicker in and out of existence faster than a blink. In the universe's first trillionth of a second, these microscopic fluctuations held the blueprint for everything we see today. Imagine a snowflake forming around a single speck of dust. That's how the cosmos built galaxies, on seeds smaller than atoms, stretched to cosmic proportions by inflation's explosive expansion. Satellite maps of the cosmic microwave background, like those from Planck, reveal this directly. The faint temperature variations we see are the amplified echoes of those quantum ripples, frozen in time 13.8 billion years ago. But not everyone agrees quantum fluctuations tell the whole story. Some theories argue that topological defects, cosmic knots in spacetime left over from the early universe, could have seeded galaxies instead. These defects, like cosmic strings or domain walls, would have created dense regions purely through their geometry, bypassing quantum mechanics entirely. Yet observations haven't found evidence for such structures, while quantum predictions match the cosmic microwave background's patterns with eerie precision. The debate isn't settled, but the scales tip toward quantum origins, a universe where galaxies owe their existence to the same physics governing subatomic particles. Here's where it gets wilder. Those primordial seeds didn't just dictate where galaxies would form, they influenced how they behave. Simulations show that galaxies born in denser initial fluctuations grow faster, their gravity pulling in more gas and dark matter. Meanwhile, galaxies in sparser regions struggle to gather material, remaining small and isolated. It's as if the universe played a game of cosmic dice at its birth, and the rolls determined which galaxies would become titans and which would fade into obscurity. Yet another player enters the scene: cosmic rays, high-energy particles racing through space at nearly light speed. These aren't just passive travelers. They can heat gas in galaxies, preventing it from collapsing into stars, or even drive winds that strip galaxies of their star-forming fuel. In clusters like the Perseus cluster, cosmic rays might help sustain the immense pressure that keeps hot gas from cooling and flooding galaxies with new stars. The universe's largest structures, it seems, are shaped not just by gravity's pull, but by the relentless rain of particles forged in supernova and black hole jets. The story of galaxy formation isn't written in gravity alone. It's a symphony of quantum beginnings, inflationary stretching, and particle bombardment. From the tiniest fluctuations to the highest energy rays, every force leaves its mark. And as we peer deeper, we're left with a humbling thought. The galaxies we admire through telescopes are the grown-up versions of quantum whispers, echoes of a time when the entire universe was no larger than a single atom. Cosmic rays are more than just streaks of energy. They're galactic sculptors, their relentless bombardment stirring gas clouds like invisible spoons, preventing them from settling into star-forming calm. Picture a pot of water on a rolling boil. The bubbles keep it from freezing, no matter how cold the room. That's what cosmic rays do to galactic gas. Their high-energy chaos injects turbulence, disrupting the delicate balance needed for gravity to pull matter into stars. In galaxies like Messier 87, where a supermassive black hole spews jets packed with cosmic rays, astronomers have observed vast regions where gas remains too agitated to collapse, leaving stellar nurseries eerily silent. The link between cosmic rays and red and dead galaxies, those aging giants where star formation has ceased, is no coincidence. Studies of galaxy clusters like Coma reveal that the most massive ellipticals, their star-making fuel exhausted, also bathe in intense cosmic ray showers. These rays likely originate from active galactic nuclei, where black holes accelerate particles to near light speeds. As those particles escape into the galaxy, they heat surrounding gas, rendering it too energetic to coalesce. It's a cosmic feedback loop. The more a black hole feeds, the more cosmic rays it produces, and the more effectively it shuts down its own galaxy's future star birth. Yet cosmic rays don't act alone. Paired with magnetic fields, they can create sprawling pressure fronts, pushing gas outward like a relentless wind. In starburst galaxies like NGC 253, where stars explode in rapid succession, cosmic rays and magnetic fields combine to drive colossal outflows, stripping away the raw material for new stars. Some theories suggest this might explain why certain galaxies age prematurely, their stellar factories dismantled from within by the very energy their brightest stars produce. But here's the twist: cosmic rays might also be galactic fertilizers. In low-density regions, their ionization could actually help gas cool by breaking apart molecules, allowing gravity to eventually take over. It's a paradox. The same force that stifles star formation in one galaxy might quietly nurture it in another. The key lies in dosage. Too many cosmic rays and gas stays turbulent, just enough, and they might set the stage for slow, steady star birth. This dance of destruction and creation hinges on baryonic matter, the ordinary atoms that make up stars, planets, and us. Yet baryons are the universe's great underachievers, accounting for less than 5% of its total content. Why do they clump so precisely into galaxies, while dark matter and energy dominate the cosmos? The answer might lie in cosmic rays' ability to redistribute baryons, pushing them into dark matter's gravitational embrace or scattering them into the void. One thing's certain: to understand galaxies, we must first unravel why the universe's rarest ingredient, the stuff of stars and life, behaves so unpredictably in the face of invisible forces. Baryonic acoustic oscillations sound like something from a physicist's fever dream, but they're actually the universe's oldest fingerprints, frozen echoes of sound waves that rippled through the cosmos when it was a seething plasma soup. Picture the early universe as a colossal bell struck by the Big Bang itself. Those vibrations raced outward at half the speed of light, compressing matter into dense shells before inflation stretched them to cosmic scales. Today, those ancient ripples aren't heard, they're seen, etched into the clustering of galaxies like concentric rings in a tree trunk. The Sloan Digital Sky Survey's galaxy maps reveal this stunning pattern. Galaxies are slightly more likely to be separated by roughly 500 million light-years, a relic of that primordial sonic boom. But here's what's wild: these oscillations aren't just fossils. They might still be shaping galaxies today. Simulations suggest that the overdense regions left by those sound waves became gravitational wells, pulling in gas and dark matter to form the first proto-galaxies. Over billions of years, mergers and growth obscured the original pattern, but traces linger. In the Pisces Cetus supercluster complex, one of the largest known structures, astronomers have detected a faint but statistically significant alignment of galaxies matching the acoustic scale. It's as if the universe's first symphony never truly ended. Its rhythm still guides where galaxies gather. The real power of baryonic acoustic oscillations lies in their precision. Unlike other cosmic yardsticks, their scale is imprinted so deeply in spacetime that they serve as a standard ruler for measuring the universe's expansion. When astronomers found these oscillations appeared slightly larger in distant galaxies, it confirmed dark energy's accelerating push, a discovery that earned the 2011 Nobel Prize. Yet some researchers argue we're missing part of the story. Could these oscillations also explain why certain galactic voids seem unnaturally empty? or why some filaments in the cosmic web appear more sharply defined than simulations predict. Now shift your gaze from sound to gravity itself. What if our understanding of this fundamental force is incomplete? The next theory dares to ask whether gravity behaves differently on cosmic scales, bending the rules we thought were set in stone. Could modified gravity explain galactic rotations without invoking dark matter? Or does it unravel more mysteries than it solves? The answer might rewrite physics itself. Newton and Einstein gave us gravity's rulebook, but what if galaxies are playing by different rules entirely? Enter modified Newtonian dynamics, or MUND, a theory that tosses out dark matter's invisible crutch and says we've misunderstood gravity all along. Picture a car speeding around a curve. Newton says it should slow down unless an unseen force grips it, but MUND argues the curve itself changes shape at galactic scales, making the car's speed natural. This isn't just tweaking equations, it's suggesting gravity weakens less than expected over vast distances, eliminating the need for dark matter to explain why stars orbit galaxies faster than predicted. The evidence comes from those infamous flat rotation curves. In spiral galaxies like NGC 3198, outer stars whirl just as fast as inner ones, defying Newton's laws unless dark matter's halo is invoked. Yet MUND adjustments to gravity's math predict these curves eerily well. No invisible particles required. Even more compelling are ultra-diffuse galaxies like Dragonfly 44, which appear almost devoid of dark matter yet still follow MUND predictions. For proponents, this is Occam's razor in action. Why invent mysterious matter when tweaking gravity solves the puzzle, but skeptics fire back? If MUND is right, why do galaxy clusters like the Bullet Cluster show mass separated from visible matter, seemingly proving dark matter's existence? MUND supporters counter that even their model needs some unseen mass in clusters, though far less than standard cosmology requires. Others point to cosmic microwave background patterns, which align exquisitely with dark matter models. MUND tweaks struggle here, forcing awkward add-ons that critics call patchwork fixes. The debate gets philosophical. Is it simpler to rewrite gravity's laws or populate the cosmos with undetectable particles? Yet MUND boldness has inspired even bolder ideas. What if gravity's apparent changes hint at something deeper, like the universe operating as a cosmic hologram, where the 3D world we see is just a projection of information encoded on a 2D surface? This isn't science fiction, it's the holographic principle, a radical framework where gravity itself might emerge from quantum data, flickering at the universe's edges. And if true, it wouldn't just challenge dark matter, it could redefine reality itself. The holographic principle turns reality inside out. What if galaxies aren't three-dimensional objects at all, but ghostly projections, like shadows cast by information etched on the edge of the cosmos? Imagine a movie screen where every star, every spiral arm, is just a pixel in a cosmic film, its true source hidden in a two-dimensional code we can't see. This isn't science fiction. It's a radical theory born from black hole physics, where the entropy of a black hole's event horizon suggests all information within it might be encoded on its surface. Scale that up, and the universe itself could be a hologram, with galaxies merely elaborate illusions. The math is tentative but tantalizing. Equations derived from string theory and quantum gravity hint that space-time might emerge from entangled quantum bits on a distant boundary, like a 3D image rendered from a 2D pattern. If true, the shape of a galaxy wouldn't be defined by gravity or dark matter alone. It'd be a translation of data, a cosmic mirage whose structure depends on how information is processed at the universe's edges. Supporters point to oddities like the way certain quantum systems scale with surface area rather than volume, as if reality cares more about boundaries than interiors. Yet the implications are dizzying. If the holographic principle holds, then galactic collisions, star formation, even the cosmic web might be secondary phenomena, epiphenomena of deeper information processing. A black hole's jet or a spiral galaxy's arms could be the universe's way of displaying data, like a glimmer on a screen. Critics argue this explains nothing concrete, but proponents counter that it reframes everything. Dark matter's grip, dark energy's push. Even the nature of time might stem from how information is stored and updated on the cosmic horizon. Philosophically, it's a thunderclap. It suggests that the universe isn't just described by mathematics, it is mathematics, a computation unfolding on a hidden surface. The Milky Way's grandeur, then, would be no more tangible than a character in a video game, its motions dictated by code we're only beginning to decipher. But if galaxies are projections, what's projecting them? The answer might lie in the vacuum itself, not empty space, but a seething quantum foam where particles flicker in and out of existence, each fluctuation a brushstroke on the hologram's canvas. This brings us to an even more elusive architect, vacuum energy, the latent power hidden in seemingly empty space. Could this quantum static be the ink with which the universe writes its holographic code? The line between science and speculation blurs here, but one thing's clear: the forces shaping galaxies might not be forces at all, but whispers from a deeper reality where information, not matter, is the true currency of the cosmos. Vacuum energy isn't empty space, it's a seething quantum foam, where particles flicker in and out of existence so fast they defy measurement. Picture a pot of water at a rolling boil, its surface erupting with bubbles that form and pop in an instant. Now shrink those bubbles down to the Planck scale, 1 billion trillion times smaller than an atom, and you've got the fabric of spacetime itself, a frothing, chaotic sea of virtual particles that borrow energy from the universe just long enough to leave their mark. This isn't poetic exaggeration, it's quantum field theory's startling prediction, and it might hold the key to why galaxies look the way they do. Here's the wild part: those fleeting quantum bubbles could be nudging cosmic structure into existence. Just as bubbles in boiling water create larger convection patterns, vacuum fluctuations might imprint tiny irregularities on the early universe's density field. Over billions of years, gravity amplifies those microscopic ripples into vast galactic scaffolds. Some models even suggest that certain ultra-diffuse galaxies, those faint, wispy structures with far fewer stars than expected, could be fossils of regions where vacuum energy's chaotic churn suppressed normal matter clustering. It's as if the universe's smallest scale frenzy wrote its signature on the largest structures we see today. Yet direct evidence remains elusive. Vacuum energy's effects are drowned out by gravity's roar on galactic scales, like trying to hear a whisper in a hurricane. But subtle hints linger. The cosmological constant, that mysterious number driving the universe's accelerated expansion, might be vacuum energy's macroscopic shadow, a cumulative effect of countless quantum fluctuations. And in the precise alignment of galaxy spins, some theorists detect a faint statistical preference that could trace back to quantum foam's primordial influence. The real twist: time itself might be part of this quantum sculpting. Just as vacuum fluctuations warp space, they could also create microscopic time delays, stretching or compressing moments on scales so small we'd never notice. But over cosmic epochs, these temporal ripples might subtly alter how galaxies accumulate mass, like a clock that ticks slightly differently in deep space versus near a supercluster. The end result could be galaxies that evolve not just by gravity's rules, but by the hidden stopwatch of quantum time. This blurs the line between the very small and the unimaginably large, suggesting that galactic majesty might spring from spacetime's tiniest tremors. Whether vacuum energy's fingerprints are real or just mathematical phantoms remains one of cosmology's deepest puzzles, one that forces us to ask, is the universe shaped by forces we can see, or by the ghostly hum of nothingness itself? What if the universe's rulebook wasn't always the same? The 15th theory dares to suggest that fundamental forces, gravity, electromagnetism, even the strength of atomic bonds, might have been dialed up in the cosmos' youth, subtly altering how galaxies took shape. Picture gravity flexing its muscles in the early universe, pulling gas clouds together with a grip 10% stronger than today. Galaxies would have formed faster, denser, their stars igniting in a frenzied rush. We're not just talking about tweaking cosmic history, we're rewriting physics itself. The evidence comes from quasars, those brilliant beacons whose light spent billions of years crossing the universe. When astronomers analyze their spectra, they're glimpsing snapshots of ancient chemistry. Some studies claim to detect slight shifts in the fine structure constant, a number governing electromagnetism, when comparing quasar light to lab measurements. If confirmed, it would mean electrons and protons interacted differently in the past, potentially changing how atoms formed and how stars burned. Imagine early galaxies where nuclear fusion ran hotter, forging heavier elements sooner, or where magnetic fields gripped gas clouds with unfamiliar intensity. But the debate rages. Skeptics argue these quasar signals could be illusions, distorted by interstellar dust or quirks in the data. Others propose even wilder ideas. What if gravity itself weakened over time? Modified gravity theories like MAN suggest this could explain dark matter's ghostly effects without inventing new particles. Yet tampering with constants opens Pandora's box. If gravity was stronger in the past, why didn't the universe collapse back on itself sooner? And how do you reconcile varying constants with the cosmic microwave background's near-perfect uniformity? The implications spiral outward. If constants drift, then galaxies aren't just evolving their products of a shifting playing field, they're forms locked to the era of their birth. Early galaxies might be fundamentally alien, their stars obeying different nuclear recipes, their black holes growing under unfamiliar gravitational rules. Even dark energy's acceleration could be reinterpreted, not as a mysterious repulsive force, but as the gradual dilution of gravity's grip over cosmic time. This leads us to an even more radical vision: fractal galaxies. If the universe's constants fluctuate not just through time but across space, could galaxy formation follow patterns that repeat at different scales? Imagine zooming into a spiral arm to find miniature versions of the whole galaxy, each with its own self-similar structure, a cosmic matryoshka doll where the same forces shape both the grandest designs and their tiniest echoes. Some astronomers argue galaxy clusters already hint at this, their distributions mirroring the arrangement of stars within individual galaxies. But fractals aren't just about appearance, they suggest universal processes operating across scales. Turbulence in interstellar gas, the branching of cosmic filaments, even the distribution of dark matter halos might follow fractal mathematics, revealing hidden order in apparent chaos. Whether driven by varying constants or deeper symmetries, this idea challenges us to see galaxies not as isolated islands, but as interconnected expressions of a cosmos where the rules themselves are still being written. Fractal cosmology turns the universe into a cosmic kaleidoscope. What if galaxies aren't randomly scattered but arranged in patterns that repeat themselves, like intricate Russian nesting dolls at every scale? Imagine zooming out from a single spiral galaxy to see its structure echoed in the swirling arms of a galactic supercluster. then zooming out further to find that same spiral motif repeated across the entire observable universe. This isn't just artistic whimsy, it's a radical challenge to cosmology's bedrock assumption that on the largest scales, the universe is smooth and homogeneous like a well-mixed batter. Proponents of fractal cosmology argue instead that the cosmos is lumpy all the way up, with galaxies clustering in self-similar hierarchies that defy traditional scaling laws. The idea traces back to mathematician Benoit Mandelbrot, who famously asked, "How long is the coast of Britain?" The answer depends on your ruler's scale. The finer you measure, the longer it gets. Apply that logic to galaxies, and you get the fractal universe hypothesis. No matter how far you zoom in or out, the distribution of matter follows the same statistical pattern. Some galaxy surveys, like the Sloan Digital Sky Survey, initially seemed to support this. When researchers analyzed galaxy counts in ever larger volumes, they found correlations that didn't vanish as expected, hinting at structure persisting across billions of light years. Yet mainstream cosmology pushes back hard. The cosmic microwave background, that fossilized glow from the infant universe, appears remarkably uniform, supporting the idea of large-scale homogeneity. Simulations of dark matter evolution also show fractal-like clustering at smaller scales, but this cosmic web supposedly smooths out past a few 100 million light-years. Critics argue that apparent fractal patterns are just temporary, a phase in the universe's evolution before gravity erases them. Others counter that we're seeing selection bias. Our telescopes might not yet probe deeply enough to confirm or refute fractals definitively. The debate isn't just academic, it cuts to the heart of how we measure the universe. If the cosmos is fractal, standard yardsticks like redshift distances could be flawed, and dark energy's inferred acceleration might need re-evaluation. Even the Big Bang's narrative could shift. Perhaps inflation, that explosive early expansion, didn't homogenize the universe as thoroughly as we thought. Fractal advocates point to oddities like the Hercules Corona Borealis Great Wall, a colossal galaxy filament stretching 10 billion light-years, as evidence that maximum structure size might not exist. But for all its mathematical elegance, fractal cosmology struggles with physics. Gravity alone can't explain infinite self-similarity. You'd need new forces or primordial conditions beyond current models. And then there's the Occam's razor problem. Is it simpler to accept a fractal universe or to tweak existing theories to explain anomalies? The answer might lie in plasma cosmology, a rival framework where electrified gas, not just gravity, shapes galaxies in ways that could mimic fractals. Because if there's one thing the cosmos loves, it's reminding us that the rules we take for granted might just be local bylaws in an infinite, ever-surprising universe. Plasma isn't just the stuff of stars, it might be the invisible hand sculpting galaxies themselves. While gravity gets all the attention, there's a radical theory that says electromagnetism, coursing through ionized gas, could be the true architect of galactic shapes. Picture a spiral galaxy not as a gravity-bound whirlpool, but as a cosmic circuit, its arms tracing the paths of billion light-year-long electric currents. Lab experiments with plasma chambers add fuel to this fire. When researchers pass electrical discharges through ionized gas, they've created uncanny replicas of spiral arms, jets, and even galactic filaments, all without invoking dark matter or gravity's pull. The plasma universe hypothesis flips conventional cosmology on its head. Proponents argue that 99% of the observable universe is plasma-charged particles responding to electromagnetic forces, so why wouldn't those forces dominate? They point to galaxies like NGC 4747, where tidal tails inexplicably glow with synchrotron radiation, a telltale sign of intense magnetic activity. Or consider the Virgo cluster's galaxies, whose alignment along vast magnetic fields suggests electricity might be herding them like charged sheep. Even the Milky Way's own Fermi bubble's colossal gamma-ray structures erupting from its core could be remnants of a galactic-scale discharge, a lightning bolt spanning 50,000 light-years. Mainstream cosmology isn't convinced. Critics highlight gaps, like how plasma models struggle to explain the precise rotation curves of dwarf galaxies or the cosmic web's dark matter scaffolding. And while lab plasmas mimic galactic shapes, scaling those experiments up to cosmic dimensions requires leaps in theory. Yet plasma advocates counter that we've underestimated electromagnetism's reach. They point to Birkeland currents, those twisting rivers of charged particles snaking through space, as possible power lines feeding galaxies along intergalactic circuits. If true, dark matter's gravitational grip might be a mirage, masking the true force wiring the cosmos together. The debate isn't just academic, it reshapes how we see our place in the universe. If galaxies are electromagnetic phenomena, their diversity could reflect local plasma conditions rather than gravitational history. Starburst galaxies might be short-circuiting, their frenzied star birth sparked by electrical surges. Elliptical galaxies could be discharged relics, their plasma energy spent. Even black holes might transform from gravity wells into cosmic electrodes, their jets powered by galactic-scale currents. But here's the twist. Whether gravity or plasma rules, both roads lead to an eerie question: why does any of this allow for us? That's where the Anthropic Principle enters, the idea that the universe's laws seem fine-tuned to permit life. If electromagnetism dominates, why did it forge galaxies capable of nurturing stars with stable, life-friendly planets? The answer might lie in a cosmic balancing act where forces, whether gravitational or electric, conspire to create islands of order in a sea of chaos. Because in the end, every theory of galaxy formation must reckon with one undeniable fact: we're here to observe them, and that observation might be the most profound clue of all. The Anthropic Principle throws a cosmic curveball. What if galaxies look the way they do simply because no other form could have produced beings capable of observing them? Imagine a universe where spiral arms never formed, where gas collapsed into featureless blobs or scattered into chaotic fragments. In those hypothetical realms, would there be planets stable enough for life to arise? Or are the majestic structures we see, the spirals, the ellipticals, the delicate balance of star formation, inevitable prerequisites for consciousness itself? This isn't just idle speculation. It's the anthropic selection effect, the idea that our very existence filters the kinds of galaxies we're able to witness. Consider the Milky Way's quiet suburbs, a region neither too close to the violent galactic core nor too far out in the star-poor halo. Here, stable orbits allow planets like Earth to exist for billions of years, undisturbed by lethal radiation or gravitational upheaval. If most galaxies lacked such Goldilocks zones, would life ever get a foothold? Even the abundance of heavy elements forged in stellar furnaces and scattered by supernova seems fine-tuned for complexity. Too few metals and rocky planets never form, too many, and radiation sterilizes potential biospheres. The galaxies we see might be a biased sample, their structures reflecting not just physics but the silent imperative of permitting observers. Now stretch this logic to the multiverse. If countless universes exist with different physical constants, most might produce galaxies too chaotic or sterile for life. We find ourselves in one where the numbers align, where dark matters pull and dark energies push conspire to create galactic nurseries capable of nurturing intelligence. Does that mean other, stranger galaxies exist in unseen universes, vast, swirling monstrosities where time flows backward, or frozen, crystalline structures where entropy reverses? The Anthropic Principle doesn't answer these questions, it amplifies them, blurring the line between science and philosophy. Critics argue this reasoning borders on tautology. We see certain galaxies because we're here to see them. But supporters counter that it's a profound selection bias, like a fish concluding water is universal because it's never left the ocean. Either way, the implications unsettle our cosmic confidence. If galactic structure is entwined with life's potential, does that mean the universe is somehow meant for observers? Or is it just a statistical fluke, one outcome in an infinite sea of failed experiments? This dilemma leads us to an even deeper mystery. What if the forces shaping galaxies aren't just fine-tuned but arise from symmetries we've yet to uncover? Enter supersymmetry, a theory where every known particle has a hidden twin, and these shadowy partners might hold the key to dark matter's identity, and thus to the very architecture of galaxies. Because if the cosmos is a mirror reflecting hidden dimensions of reality, then the galaxies we admire might be more than celestial accidents. They could be clues pointing toward a symmetry so profound it underpins existence itself. Supersymmetry whispers an elegant solution to dark matter's riddle. What if every particle we know has a hidden twin, and one of those twins is the universe's missing mass? This isn't science fiction. It's the promise of supersymmetry, a theory where electrons, quarks, and even photons could have undiscovered counterparts with bizarre properties. Among these hypothetical siblings, the neutralino stands out, a heavy, sluggish particle that rarely interacts with light or matter, making it a perfect candidate for dark matter's elusive identity. Picture a cosmic game of hide and seek where trillions of these invisible particles drift through your body every second, their collective gravity sculpting galaxies while leaving no trace beyond their pull on stars. But neutralinos aren't the only players. For decades, physicists pinned hopes on WIMP weakly interacting massive particles, predicting they'd reveal themselves in ultra-sensitive detectors buried deep underground. Yet experiment after experiment, from the Large Hadron Collider to cryogenic labs in abandoned mines, has come up empty. Actions, another theoretical dark matter particle, offer a tantalizing alternative. These ultra-lightweight particles could flow through the cosmos like a ghostly quantum fog, their wave-like nature potentially explaining why some dwarf galaxies appear less clumpy than dark matter models predict. The twist: actions might transform into detectable photons in strong magnetic fields, giving experiments like the Action Dark Matter experiment a fighting chance to spot them. Supersymmetry's allure lies in its mathematical beauty. It doesn't just explain dark matter, it solves half a dozen cosmic puzzles at once. By balancing the quantum equations of particle physics, it prevents them from spiraling into absurdity at high energies. Yet for all its elegance, nature seems to be withholding confirmation. The LHC's failure to spot supersymmetric particles has left theorists scrambling, tweaking models to push these hypothetical twins just beyond our current reach. Some argue we're on the verge of discovery. Others whisper that supersymmetry might be a dead end, its pristine symmetry too perfect for our messy universe. The plot thickens when extra dimensions enter the scene. If supersymmetry's particles are hiding, could they be lurking in higher spatial dimensions curled up at scales too tiny to probe? String theory suggests these dimensions might act like cosmic attics, storing particles we can't perceive directly. In such a universe, dark matter wouldn't just be invisible, it could be literally out of reach, its influence leaking into our three-dimensional world like shadows on a cave wall. Whether through supersymmetry, hidden dimensions, or something even stranger, the search for dark matter's identity forces us to confront a humbling truth. The galaxies we see are just the visible ink on a page written in invisible ink, and decoding their full story might require rewriting physics itself. What if dark matter doesn't exist at all, and the real explanation for galactic rotation lies in dimensions we can't see? Higher dimensional gravity dares to rewrite the rules, suggesting that what we perceive as gravity's weakness might actually be its escape. Picture a garden hose lying flat on the ground. From a distance, it looks one-dimensional, but step closer, and you realize it's a cylinder with hidden breadth. Similarly, our universe might be a three-dimensional brain, floating in a higher dimensional space, with gravity's influence seeping out into these unseen realms like water through a sieve. This isn't just wild speculation. It's the heart of brain world models where galaxies' rotation anomalies could stem from gravity's lost strength, not invisible matter. Take the Randall-Sundrum model, a theoretical framework where our universe is a four-dimensional membrane embedded in a five-dimensional bulk. In this scenario, gravity behaves differently at galactic scales because its field lines stretch into the extra dimension, diluting their pull on stars orbiting a galaxy's edge. The result: stars move faster than expected, mimicking the effects of dark matter without requiring unseen particles. It's as if a magician's invisible strings were simply hidden in a dimension beyond our sight. Even Einstein's equations hint at this possibility. General relativity doesn't forbid extra dimensions. It just assumes they're too small to matter. But what if they're not small, just inaccessible? The allure is undeniable. Brain world models elegantly sidestep dark matter's biggest hurdle, the decades-long failure to detect its particles, yet the trade-off is stark. If gravity leaks into extra dimensions, why don't we see other forces like electromagnetism doing the same? And how do you test a theory where the smoking gun, the higher dimensions themselves, lies forever beyond observation? Critics argue this swaps one mystery for another, trading dark matter's invisibility for untestable geometry. Supporters counter that math itself might be the evidence. Certain brain world predictions align galaxy rotation curves as precisely as dark matter models, all without inventing new particles. This dilemma leads to an even more radical idea. What if gravity isn't fundamental at all? Emergent gravity, proposed by physicist Eric Verland, suggests that gravity, like temperature or pressure, isn't a force but a side effect of deeper physics, emerging from the quantum entanglement of spacetime's building blocks. In this view, galactic rotation anomalies arise not from hidden matter or dimensions, but from entropy, the universe's innate tendency toward disorder. Imagine a galaxy's outer stars responding to an invisible, thermal gradient in spacetime itself, their motion dictated by information encoded at the universe's edges. It's a paradigm shift so profound it redefines gravity from cosmic glue to cosmic illusion. The implications ripple outward. If emergent gravity holds, dark matter's fingerprints might actually be the holographic shadows of quantum data, a cosmic mirage woven into the fabric of reality. Yet, like brain world theories, empirical proof remains elusive. Both ideas share a tantalizing trait. They replace the what of dark matter with the how of spacetime's hidden layers. Whether through hidden dimensions or emergent laws, the message is clear: our understanding of gravity, the force that shaped galaxies, might be missing a dimension. Literally, emergent gravity turns everything we thought we knew about cosmic forces upside down. What if gravity isn't a fundamental force at all, but a side effect, an illusion emerging from the chaotic dance of quantum information? Picture a bustling city where traffic patterns aren't dictated by street signs, but by the collective decisions of millions of drivers. In the same way, gravity might not be a standalone force but a statistical outcome, the universe's way of averaging out the microscopic tangles of quantum entanglement. This radical idea, championed by physicist Eric Verland, suggests that what we perceive as gravity's pull, especially in galaxies, is actually spacetime's response to entropy, a cosmic tendency toward disorder encoded at the universe's edges. The evidence comes from galactic rotation curves, those stubborn discrepancies where stars orbit too fast for gravity's textbook predictions. Dark matter has long been the go-to explanation, but emergent gravity offers a daring alternative. The extra pull isn't from invisible matter, but from the way entangled quantum bits on the boundary of space generate an entropic force. Think of it like a cosmic version of osmosis. Stars at a galaxy's edge aren't being tugged by dark matter's halo, but are responding to an invisible gradient in spacetime's information content. It's as if the universe has a hidden ledger and gravity is just the ink bleeding through the pages. Critics pounce on two fronts. First, emergent gravity struggles to explain the bullet cluster, where colliding galaxies seem to have left their dark matter behind, a smoking gun for particle-based theories. Second, entropy-based models rely on holographic principles that remain mathematically speculative. Yet supporters counter that emergent gravity naturally explains why galaxies of similar sizes have similar rotation curves, a coincidence dark matter models must fine-tune. Even more compelling, it eliminates the need for undiscovered particles, offering an elegant Occam's razor solution. Gravity isn't weak because it leaks into extra dimensions or hides in particles. It's weak because it's not fundamental at all. The debate hinges on a deeper question: is the universe built from tangible stuff or abstract information? If emergent gravity holds, then galaxies aren't just shaped by forces, but by the universe's hidden accounting system, where every star's motion is a transaction in a cosmic data network. But before we rewrite physics textbooks, there's another contender lurking in the shadows: primordial black holes, relics from the universe's first second that could be hiding in plain sight as dark matter. These ancient gravitational traps might not just reframe galaxy formation, they could rewrite cosmic history itself. Primordial black holes could be the universe's original architects, tiny, dense remnants of the Big Bang itself, lurking unseen in the cosmos and seeding the very first galaxies. Imagine a universe only seconds old, a seething cauldron of energy where quantum fluctuations created microscopic knots of spacetime so intense they collapsed into black holes no larger than an atom yet as massive as a mountain. These primordial relics wouldn't just sit idle, they'd sink into the earliest clumps of dark matter and gas, their gravity acting like cosmic anchors, pulling matter together faster than gravity alone could manage. In this scenario, galaxies didn't form randomly. They grew around these ancient black holes like pearls around grains of sand. The smoking gun might lie in gravitational waves. When LIGO detected mergers of unexpectedly heavy black holes, some 30 times the Sun's mass, it raised eyebrows. Conventional stellar collapse shouldn't produce so many hefty black holes, but primordial origins could explain their abundance. Even more tantalizing are the ultra-fast mergers, where black holes spiral together in months rather than billions of years. If primordial black holes swarm galactic halos, frequent close encounters could trigger these rapid collisions, leaving behind the supermassive black holes we now see anchoring galaxies. The math is compelling. A few primordial seeds per galaxy could merge over eons, growing into the monsters like Sagittarius, a star at the Milky Way's heart. Yet the plot twists further. Some theories suggest these primordial black holes didn't just seed galaxies, they might be dark matter. If enough of them formed in the early universe, their combined mass could account for the missing gravitational pull without invoking exotic particles. It's an elegant 2-for-1 solution, tiny black holes as both galaxy builders and the universe's invisible scaffolding, but critics point to glaring gaps. Where are the telltale microlensing events, the flashes of light as primordial black holes warp starlight? Surveys like OGLE have found far fewer than predicted, leaving the idea in limbo. Now, stretch the imagination further. What if these black holes didn't form from quantum chaos but were forged by cosmic strings, infinitely thin threads of energy left over from the universe's birth? These hypothetical defects in spacetime could have kinked or looped, creating regions so dense they birthed black holes directly. Cosmic strings wouldn't just explain primordial black holes, they'd weave them into a larger tapestry, connecting galaxies along invisible filaments like beads on a necklace. The universe's grand design, then, might be written not just in gravity or dark matter, but in the echoes of defects woven into spacetime itself. Cosmic strings sound like science fiction, infinitely thin threads of pure energy, thinner than an atom yet stretching across the entire universe, left over from the fiery chaos of the Big Bang. Picture them as cracks frozen in spacetime itself, relics of a phase transition when the cosmos cooled from unimaginable energies into the familiar forces we know today. These aren't just theoretical oddities. If they exist, they'd be cosmic puppeteers, warping galaxies along their lengths like beads on an invisible wire. Their gravitational pull would be so intense that even a single string could slice through a galaxy, bending light around it in telltale arcs, an effect astronomers call gravitational lensing. Some researchers argue we've already spotted their fingerprints. Take the peculiar double images of distant quasars, where a single light source appears duplicated in the sky. Conventional dark matter models struggle to explain certain asymmetries in these splits, but a cosmic string drifting between us and the quasar could produce the exact distortion observed. Even more intriguing are reports of unexplained linear anomalies in the cosmic microwave background, faint, straight-line temperature variations that some theorists interpret as strings brushing against the infant universe, leaving scars in its oldest light. Yet mainstream cosmology remains skeptical. Cosmic strings demand conditions so extreme they might only form in specific inflationary models, and no direct detection has been confirmed. Critics point out that lensing anomalies could stem from more mundane causes, like rogue black holes or uneven dark matter distributions, the biggest hurdle. Strings should vibrate, sending out gravitational waves detectable by observatories like LIGO. So far, the cosmos has stayed silent, but here's the twist. If cosmic strings are real, they might not just warp galaxies, they could be their backbones. Some theories suggest these spacetime defects acted as cosmic scaffolding in the early universe, channeling gas and dark matter into dense filaments where galaxies preferentially formed. It's a haunting thought. The Milky Way might not just float in space but be threaded onto an invisible string, its very existence tied to a defect older than time. This idea of hidden structures shaping the cosmos doesn't end with strings. What if another phantom, faster than light tachyonic fields, also left its mark on galaxies? These hypothetical particles, forever racing against the speed limit of the universe, could have imprinted their energy on galactic scales, leaving behind patterns we're only beginning to decode. The line between wild speculation and groundbreaking physics has never been thinner. Tachyonic dark energy dares to break the universe's ultimate speed limit. What if the force accelerating cosmic expansion isn't just mysterious but faster than light itself? Picture a shadowy field permeating all of space, its particles tachyons racing endlessly at speeds no ordinary matter can match. Unlike anything in our experience, these hypothetical entities wouldn't slow down as the universe expands. They'd gain energy, pushing galaxies apart with ever-increasing fervor. The result, an expansion so violent it could warp galactic shapes over time, stretching spiral arms into distorted tendrils or flinging stars from their orbits like sparks from a wheel. The math is as elegant as it is unsettling. Tachyonic fields emerge from string theory's equations as a possible dark energy candidate. Their negative pressure capable of driving accelerated expansion without invoking a cosmological constant. Some models even suggest these fields could interact with dark matter, creating feedback loops where galactic halos grow increasingly asymmetric as tachyons transfer momentum to invisible particles. Imagine a galaxy like Messier 94, its outer disk mysteriously warped, not by collisions but by the unseen drag of a tachyonic wind. Yet for all its theoretical allure, tachyonic dark energy remains ghostly. No telescope has detected its signature, no anomalous particle tracks in detectors, no telltale distortions in the cosmic microwave background. Critics argue this absence is damning. If tachyons permeate space, why haven't their fluctuations left ripples in the large-scale structure of the cosmos? Supporters counter that tachyons might couple so weakly to ordinary matter that their effects emerge only on cosmological scales, like whispers drowned out by the roar of a hurricane. This speculative dance leads to an even wilder possibility, a bouncing universe. If tachyonic fields grow too dominant, they could someday reverse cosmic expansion, collapsing spacetime until quantum effects trigger a rebound, a new Big Bang from the ashes of the old. Galaxies in such a scenario wouldn't just fade into isolation, they'd be recycled, their matter and energy forged anew in a cycle without beginning or end. Whether tachyons are real or just mathematical phantoms, they force us to confront a universe where the rules we cherish might be local bylaws in a far stranger cosmos. What if galaxies aren't just products of a single cosmic cycle but layered artifacts, their structures imprinted with echoes of universes that came before? The 25th theory dares to imagine a cosmos without true beginnings or endings, an infinite loop where each Big Bang springs from the collapse of a prior universe, and galaxies carry subtle scars from these forgotten epochs. This is conformal cyclic cosmology, a vision where the universe's expansion doesn't end in cold isolation but resets, like a phoenix reborn from its own ashes. At the boundary between cycles, all particles lose mass due to extreme stretching, leaving only pure energy, a state called conformal invariance, before collapsing back into a new singularity. The twist: information isn't erased. Just as a vinyl record preserves sound in its grooves, galaxies might encode data from past universes in the arrangement of their stars or the geometry of their dark matter halos. Look closely at the cosmic microwave background, that fossilized glow from the infant universe. Some researchers claim to detect concentric circular patterns, possible collision scars from black holes that survived the cycle's end. Others argue galactic filaments, those vast threads weaving the cosmic web, align in ways that defy randomness, as if tracing the skeleton of a predecessor universe. Even the Milky Way's peculiar warp, its disk bending like a vinyl record left in the sun, could be a relic of gravitational tides from a long-vanished neighbor in a prior cycle. These ideas remain speculative, but they offer something profound: a universe where death isn't extinction but transformation, and galaxies serve as cosmic archivists. Now shift from cyclic echoes to a stranger possibility: holographic noise. If the universe is fundamentally a hologram, projecting three-dimensional space from a two-dimensional boundary, then galaxies might flicker with quantum static, their apparent smoothness an illusion. Every star, every spiral arm could be pixelated at the Planck scale, vibrating with information we're only beginning to decode. It's a vision where the universe isn't just shaped by forces but by data, its grandest structures rendered in the language of quantum bits. Whether through infinite cycles or holographic code, one message is clear. Galaxies might be far more than celestial objects, they could be living records, whispering secrets across time and dimensions. What if the smooth spirals and elegant curves of galaxies aren't as seamless as they appear? Beneath their grand designs, the universe might be flickering with holographic noise, a quantum static so fine it's etched into the very fabric of spacetime. Picture a high-definition screen zoomed in too far, revealing individual pixels that distort the image. Now imagine those pixels aren't on a display but woven into reality itself, each one a Planck-scale unit of information vibrating at the edge of perception. This isn't just wild speculation, it's a radical offshoot of the holographic principle, suggesting that galactic shapes aren't just sculpted by gravity or dark matter, but by the universe's underlying digital graininess. The evidence is tentative but tantalizing. Gravitational wave interferometers like LIGO aren't just hunting ripples in spacetime, they're sensitive enough to potentially detect this quantum noise. Some theorists argue that if the cosmos is a hologram projected from a two-dimensional boundary, then the resolution of that projection might leave faint artifacts in how galaxies rotate or cluster. Think of it like a cosmic JPEG compression. Spiral arms that appear smooth from afar might, at unimaginably small scales, reveal stair-step distortions aligned with the universe's fundamental pixel size. Even the distribution of satellite galaxies around the Milky Way, which often defies dark matter predictions, could reflect this hidden granularity, yet skepticism runs deep. Mainstream cosmology points out that holographic noise, if it exists, would be drowned out by quantum fluctuations far too tiny to influence galactic scales. Others counter that emergent phenomena, like how microscopic water molecules create macroscopic ocean waves, could amplify these effects over billions of years. The debate hinges on a deeper question: is spacetime truly continuous, or is it a mosaic of discrete information chunks? Future experiments aiming to measure spacetime's foaminess with atom interferometers or ultra-precise pulsar timing arrays might settle the score. What's undeniable is the allure of the idea. If holographic noise shapes galaxies, then every majestic spiral is both a celestial object and a cosmic message, its structure encoding secrets about the universe's deepest nature. But before we rewrite physics based on pixelation, there's another twist in the dark matter saga, one where invisible particles don't just pass through each other like ghosts, but collide, scatter, and interact with forces we've yet to name. The answer might lie in self-interacting dark matter, a theory where the universe's hidden scaffolding isn't silent but alive with invisible fireworks. Dark matter might not be the lone, ghostly wanderer we imagined. What if its particles crash into each other like invisible bumper cars, their collisions sculpting galaxies in ways we never expected? This is the bold claim of self-interacting dark matter, a theory where the universe's hidden mass isn't just passing through itself but engaging in a cosmic dance of scatters and rebounds. Picture a crowded subway station where people jostle and bump, creating zones of density and flow. Now scale that up to galactic proportions, dark matter particles smashing together, their interactions softening halos into fluffy clouds that cradle galaxies differently than traditional models predict. The result: spiral arms with smoother curves, dwarf galaxies that resist tidal shredding, and halos that puff up like cotton candy instead of collapsing into dense clumps. The bullet cluster offers startling evidence. When two galaxy clusters collided, their visible matter hot gas detected by X-rays piled up in the center like cars in a traffic jam. But their dark matter, mapped through gravitational lensing, sailed right through the crash site as if unaffected. At first, this seemed to support collisionless dark matter. But look closer, the dark matter's distribution is slightly offset, its edges more diffuse than expected, as if some particles did interact, creating drag. Self-interacting models replicate this nuance perfectly, simulating halos that resist sharp edges, their particles' gentle collisions smoothing out distortions like hands kneading dough. Yet the debate rages. Traditional collisionless dark matter, governed solely by gravity, excels at explaining the cosmic web's large-scale structure. Switch to self-interacting models, and simulations struggle to replicate the universe's filamentary scaffolding without fine-tuning. Critics argue the bullet cluster's offsets could stem from complex gravitational dynamics rather than dark matter collisions. But supporters counter with oddball galaxies like NGC 1052, where stars seem untethered from their dark matter anchors, a phenomenon easier to explain if dark matter particles scattered, redistributing their gravitational grip. Now imagine a compromise: sterile neutrinos. These hypothetical particles are shy cousins of ordinary neutrinos, interacting only via gravity and possibly weak nuclear forces. They'd avoid the over-clumping pitfalls of collisionless models while sidestepping the filamentary challenges of strongly interacting ones. Some theories even suggest sterile neutrinos could decay, emitting X-rays that might explain mysterious emission lines glimpsed in galaxy clusters. It's a tantalizing middle path, one where dark matter remains elusive but not entirely antisocial, its subtle interactions leaving faint traces in the light we can see. Whether through particle collisions or sterile whispers, the message is clear. Dark matter's story is far richer than we dreamed, and every galaxy holds clues to its untold chapters. Sterile neutrinos could be the universe's shyest architects, particles so reluctant to interact they make ordinary neutrinos seem like social butterflies. Yet their collective gravity might shape galaxies in ways we're only beginning to grasp. Imagine a neutrino with mass, not the featherweight versions we've detected, but a heavier cousin lurking just beyond our instrument's reach. These sterile neutrinos wouldn't just pass through planets like ghosts, they'd clump into warmer, fluffier dark matter halos, their slight but measurable interactions preventing the dense cusps predicted by traditional models. The result: galactic outskirts that rotate more smoothly, and dwarf galaxies that don't evaporate under tidal forces, mysteries that collisionless dark matter struggles to explain. The hint of their existence might be etched in X-rays. In 2014, astronomers studying distant galaxy clusters spotted an unexplained emission line at 3.5 kilo-electron-volts, a whisper of energy with no obvious source. Sterile neutrinos could be the culprits. If they occasionally decay, they'd emit X-rays at precisely that frequency. It's like finding a cosmic signature on a faded document, a clue that these elusive particles might not just exist but actively decay around us. Experiments like NASA's X-ray telescope Hitomi and the upcoming XRISM mission are hunting for this signal, scanning the skies for the faint glow that could confirm sterile neutrinos as dark matter's missing piece. Yet the search is fraught with tension. Some teams claim the 3.5 kilo-electron-volt line is an artifact, a quirk of instrument noise or interstellar gas. Others argue it's real but stems from mundane atomic transitions, not exotic particles. The debate hinges on a delicate balance. Sterile neutrinos must be heavy enough to influence galaxy formation, but light enough to avoid overclumping the cosmic web. It's a Goldilocks problem: too much interaction, and they disrupt large-scale structure; too little, and they're indistinguishable from ordinary dark matter. This tightrope walk leads to an even stranger possibility. What if sterile neutrinos aren't alone in their shyness? Enter mirror matter, a theoretical shadow realm where every known particle has a doppelganger. In this hidden sector, mirror protons, electrons, and neutrinos could exist alongside ours, interacting only through gravity's faintest tug. The implications are staggering. Mirror stars might burn unseen in our own galaxy, their light invisible to our telescopes. Mirror planets could orbit mirror suns, their presence betrayed only by subtle gravitational anomalies. And mirror dark matter, far richer than sterile neutrinos alone, might weave through our universe, its gravity sculpting galaxies while remaining forever out of reach. The beauty of mirror matter is its symmetry. Just as left and right hands mirror each other, so too could our universe have a twin, its particles dancing in parallel to ours. Some theories suggest the Big Bang created equal parts matter and mirror matter, but a slight asymmetry left our sector dominant. If true, dark matter's mysteries might not stem from undiscovered particles, but from an entire shadow cosmos, its presence felt only in the way galaxies spin and cluster. Experiments like the LHC are probing this idea, searching for particles that might bridge our world and its mirror. Until then, the universe's hidden architects, whether sterile neutrinos, mirror matter, or something even stranger, remain just out of sight, their signatures written in starlight and the silent pull of gravity. Mirror matter theory spins a dizzying possibility. What if every particle in our universe has a silent twin, a shadowy counterpart inhabiting a parallel cosmos that brushes against ours only through gravity's faintest whisper? This isn't science fiction. It's a mathematically grounded hypothesis where galaxies might be tugged not just by dark matter's invisible hand, but by entire mirror stars, mirror planets, even mirror black holes drifting unseen through our own Milky Way. Picture two overlapping worlds, each oblivious to the other except for the subtle gravitational wrinkles they leave behind. When neutron stars cool faster than physics predicts, some theorists point to mirror particles leaching away their heat, like ice melting in a room you didn't realize had a hidden furnace. The clues are tantalizing but elusive. Take the neutron star Cassiopeia A, whose rapid cooling defies standard models. If mirror matter exists, its particles could collide with ordinary matter in the star's core, converting precious heat into invisible mirror photons that vanish into the parallel sector. It's as if the star has a secret drain, its energy slipping into a dimension we can't perceive. Even galactic rotation curves, those stubborn mismatches that first hinted at dark matter, might find an alternative explanation in mirror matter's cumulative gravity. Instead of a halo of WIMP or actions, galaxies could be shrouded in mirror stars, objects that emit no light but bend space-time just like their visible counterparts. Yet proving this theory is like trying to catch smoke with your bare hands. Mirror matter interacts so weakly with our world that even the most sensitive detectors see nothing. Particle colliders like the LHC hunt for anomalies, missing energy or momentum that might betray a particle's jump into the mirror realm. But so far, no definitive signal has emerged. The strongest evidence might come from the cosmos itself. If mirror matter clumps into mirror galaxies, their gravitational lensing effects could distort the light of distant quasars in ways that defy conventional dark matter models. Some astronomers are already scouring sky surveys for these ghostly fingerprints. As we near the end of our journey through galaxy-shaping theories, the wildest ideas remain. Could vacuum decay rewrite galactic physics in an instant? Might time itself flow differently in cosmic voids? the universe's boldest architects, whether mirror matter, holograms, or colliding brains, challenge us to rethink not just how galaxies form, but what reality truly is. One thing's certain, the cosmos has more secrets than we've dared to imagine, and every answer we uncover only deepens the mystery. Einstein's speed limit, the cosmic rule that nothing can outpace light, might not have always been set in stone. Variable speed of light cosmology dares to suggest that in the universe's fiery infancy, light raced across space faster than it does today, rewriting the very timeline of galaxy formation. Picture a cosmos so dense and hot that photons couldn't move freely, trapped in a plasma soup until suddenly, inflation stretched space-time thin enough for light to break free. Now imagine that initial burst wasn't just liberation but hyperspeed light traveling 10, 100, or even 1 billion times faster than its current pace. This isn't just a tweak to physics, it's a rewrite of cosmic history, compressing the era when the first galaxies could have formed from billions of years into a fleeting moment. The implications are staggering. If light speed was higher, the early universe's horizons, the maximum distance particles could influence one another, would have expanded dramatically. Regions now separated by unfathomable voids might once have been in causal contact, explaining why the cosmic microwave background looks so uniform. No need for inflation's rapid expansion. A faster speed of light could have smoothed the universe's wrinkles naturally. Some models even suggest this could resolve the horizon problem without invoking a cosmological constant, offering an elegant alternative to mainstream inflation. Yet the trade-off is steep. Tampering with light speed unravels relativity's tightly woven fabric, forcing equations like E equals mc squared to flex in ways that make physicists shudder. Mainstream cosmology pushes back hard. If light speed varied, why don't we see remnants in ancient quasar light or the delicate balance of nuclear reactions in early stars? Skeptics argue that varying constants often create more problems than they solve, like patching a leaky boat with tape. But proponents counter with tantalizing clues, like anomalies in the fine structure constant, a number tied to light speed, which some quasar studies suggest might have drifted over cosmic time. The debate is far from settled, but the persistence of variable speed of light theories hints at a deeper truth. Our understanding of physics foundations might still have cracks. Now shift from the speed of light to the nature of time itself, because if light's rules can bend, perhaps time's can too. Enter time crystals, structures that don't just exist in space but pulse in a never-ending cycle of self-repeating states, like a clock that ticks without energy input. These aren't sci-fi gadgets, they're real quantum systems first observed in labs in 2017, where atoms arranged in loops defy equilibrium by oscillating indefinitely. Imagine a galaxy's dark matter halo not as a static scaffold but as a time crystal, its particles cycling through configurations over eons, subtly altering how gravity binds stars. Or consider vacuum energy, whose quantum froth might exhibit time crystalline order, imprinting rhythmic patterns on the birth of galaxies. The connection to cosmology is speculative but electrifying. If time crystals exist on cosmic scales, they could introduce a new kind of symmetry, breaking one where time, not just space, dictates structure. Galaxies might not just be shaped by gravity's pull, but by the universe's hidden metronome, ticking in dimensions we're only beginning to perceive. Whether through variable light speed or time's crystalline echoes, the message is clear. The cosmos refuses to play by the rules we've written, and every galaxy we see might be a clue to the deeper, stranger physics we've yet to name. Time crystals shatter our most basic assumptions about matter. What if the universe hosts structures that don't just exist in space but pulse in time, repeating their patterns like cosmic clocks that never wind down? Unlike ordinary crystals where atoms arrange in repeating spatial lattices, time crystals are four-dimensional, their components oscillating between states indefinitely without energy input. Picture a galaxy's dark matter halo not as a static scaffold but as a colossal time crystal, its particles cycling through configurations over eons, subtly altering how stars orbit at the edges. This isn't just theoretical whimsy. Nobel laureate Frank Wilczek proposed the idea in 2012, and by 2017, labs had created microscopic versions using chains of ytterbium ions. But the real shocker, if time crystals can exist on galactic scales, they might imprint rhythms on cosmic evolution itself. Consider the bizarre synchrony of satellite galaxies. Dwarfs orbiting the Milky Way and Andromeda aren't scattered randomly. They're clustered in thin, rotating planes like flies trapped on a spinning dinner plate. Dark matter simulations struggle to explain this arrangement, but time crystals offer a wild alternative. What if dark matter's hidden interactions include time periodic forces, creating resonant orbits that lock satellites into coordinated dances? Even the distribution of galaxy clusters hints at cosmic rhythms. Surveys reveal quasi-regular supercluster spacing, walls and voids repeating every few hundred million light-years, as if the universe's large-scale structure were a drumhead vibrating in slow motion. The quantum gravity connection is where things get truly radical. Some theories suggest spacetime itself might crystallize at microscopic scales, with time crystals emerging as defects in its fabric. Imagine the early universe cooling from a chaotic plasma, not just forming atomic nuclei but freezing into temporal order like ice crystallizing in water. These defects could have seeded galactic filaments, their repeating cycles subtly guiding where gas pooled and stars ignited. It's a fringe idea, but the math is compelling. Certain quantum gravity models predict time crystal-like behavior in black hole horizons, where spacetime's extreme warping might sustain self-reinforcing cycles. Critics pounce on practical hurdles. Lab time crystals require precise external drives to maintain their oscillations. What's the cosmic equivalent, and how could temporal order survive the universe's violent expansion? Supporters counter that exotic fields or vacuum energy might provide the necessary drive, while quantum entanglement could preserve coherence across cosmic distances. Whether time crystals sculpt galaxies or not, their very possibility forces us to confront a deeper truth. The universe might not just have time, it could be time, a dynamic tapestry where even the most stable structures pulse with hidden rhythms. This leads us to the final, most radical theory of all, one where galaxies aren't objects in a universe but holographic projections. Their every spiral arm and star cluster a fleeting shadow cast by quantum information flickering at reality's edge. The line between science and philosophy blurs here, but the implications are undeniable. If time itself is an emergent property, then the forces shaping galaxies might not be forces at all, but echoes of a deeper, stranger physics waiting to be decoded. What if galaxies aren't just cosmic structures, but glitches in a vast simulation, digital artifacts revealing the underlying code of a reality we've mistaken for physical? This 30-second theory takes the Fermi paradox, the eerie silence of the universe despite its apparent readiness for life, and flips it into something even more unsettling: the possibility that we're living in an advanced civilization's quantum computer, where galaxies are rendered with just enough detail to fool their inhabitants. Think of a video game where distant mountains are low-resolution textures. In this cosmic simulation, spiral arms and star clusters might be optimized approximations, their patterns reflecting computational shortcuts rather than natural laws. The logic is unnervingly simple. If a civilization could harness the energy of stars to power simulations, the sheer number of hypothetical simulated universes would dwarf the one real cosmos. Statistically, we're more likely to be in one of the countless simulations than the original. Even galactic oddities like the Milky Way's strangely quiet neighborhood or the unnatural smoothness of the cosmic microwave background could be explained as processing constraints or deliberate low poly designed to save computational resources. When astronomers find galaxies aligned in mathematically perfect formations or quantum particles behaving differently when observed, some whisper, "Are these the universe's loading screens, moments where the simulation struggles to render reality seamlessly?" Philosophers split into warring camps. Simulationists point to the universe's mathematical elegance as evidence of engineered design, while skeptics argue that a simulation sophisticated enough to mimic quantum mechanics and relativity would require energy and complexity beyond any conceivable civilization. The debate straddles science and metaphysics because here's the catch: if the simulation is flawless, there's no way to test it. Like a character in a game trying to prove the existence of a player, we're trapped within the system's rules. Yet the theory's cultural resonance is undeniable. It reframes galaxies not as celestial bodies but as data structures, their beauty a side effect of algorithmic efficiency. It turns dark matter into unused variables in the code and black holes into memory sinks where information is compressed or deleted. Even the holographic principle finds a sinister parallel. The idea that our 3D universe is a projection from a 2D surface mirrors how simulations often render graphics from simplified data. As we stand at the edge of 32 galaxy-shaping theories, from dark matter's pull to time's crystalline rhythms, one truth emerges. Whether the cosmos is simulated or physical, its mysteries demand humility. Every spiral, every collision, every flicker of starlight invites us to question not just how galaxies form, but what reality really is, and whether, in the end, the universe's greatest marvel isn't its grandeur, but the fact that we're here to wonder about it at all. From dark matter's invisible scaffolding to the holographic whispers of quantum information, these 32 theories don't just compete, they intertwine, painting a cosmos far stranger and more dynamic than we ever imagined. Picture a grand cosmic orchestra where gravity conducts the strings of spacetime, dark energy pounds the drums of expansion, and plasma's electric currents hum along in harmonies we're only beginning to decipher. No single force acts alone. A spiral galaxy's graceful arms might owe their shape to dark matter's pull, magnetic field's guidance, and the lingering echoes of collisions from billions of years ago, all layered like strokes on a celestial canvas. What's astonishing isn't just the diversity of ideas, it's the patterns that emerge when we step back. Dark matter recurs like a refrain, whether as WIMP actions or primordial black holes, its gravitational signature undeniable even as its nature eludes us. Gravity, too, refuses to be pinned down, morphing from Einstein's bedrock into emergent forces, extra-dimensional leaks, or even holographic projections. And threading through it all is the tension between chaos and order, galaxies sculpted by violent mergers yet fine-tuned by feedback loops, their structures balancing on the edge of turbulence and precision. Consider the Milky Way. Its spiral arms might trace the wake of a long-vanished dwarf galaxy, their gas compressed by dark matter's tides while magnetic fields steer star formation like cosmic traffic lights. Meanwhile, its central black hole belches jets that heat surrounding gas, preventing runaway starbirth, a self-regulating mechanism that echoes across the universe. Even the voids between galaxies, once thought empty, thrum with dark energy's push and the faint hum of neutrinos, their combined influence nudging cosmic structures into place. The beauty of these theories lies in their contradictions. plasma cosmology's electric whirlpools clash with dark matter's gravitational wells, yet both predict filamentary structures eerily like the cosmic web. Supersymmetry's elegant particles remain undetected, while tweaked gravity falters in clusters, yet each captures slices of truth like blind men describing an elephant. Perhaps the universe isn't choosing one theory over another, but revealing a deeper synthesis where all play a role, their relevance shifting with scale, time, or some hidden variable we've yet to uncover. This is the frontier of cosmic understanding, not a tidy answer but a vibrant debate, a reminder that galaxies are more than collections of stars, they're laboratories for the universe's most profound mysteries. Every outlier, every anomaly, the dwarf galaxies with too little dark matter, the quasars shining too bright, the filaments aligned too precisely whispers that our models are incomplete. And that's exhilarating, because in the gaps between theories, in the places where gravity bends unexpectedly or particles refuse to appear, there's room for discovery, for the next paradigm shift that will redefine our place in the cosmos. So let's celebrate not just what we know, but how much remains wondrously unknown. The same curiosity that led ancient astronomers to trace constellations in the stars now drives us to map dark matter's webs and simulate quantum foam. Whether galaxies are holograms, simulations, or something beyond our imagination, their splendor invites us to keep questioning, probing, and marveling. After all, the universe isn't just a story of forces and matter. It's a story of us, the tiny, tenacious observers who dare to decode its grand design. From dark matter's ghostly embrace to the electrifying currents of plasma cosmology, from the holographic hum of quantum pixels to the spine-tingling possibility that we're living in an ancestor simulation, every theory we've explored isn't just a competing idea, but a unique lens through which to witness the universe's grandest ballet. Each one peels back another layer of the cosmic onion, revealing not just answers but deeper, more tantalizing questions. The beauty isn't in declaring a winner, but in the sheer diversity of imagination they represent, proof that the universe refuses to be boxed into a single narrative. Take something as seemingly settled as gravity. We've seen it reimagined as emergent noise, a holographic projection, even a leak into hidden dimensions. Dark matter, once a placeholder for our ignorance, now branches into WIMP, actions, sterile neutrinos, and mirror worlds. And just when we think we've grasped the rules, the cosmos throws us a curveball like galaxies rotating too fast, or dwarf galaxies aligning in planes that defy supercomputer simulations. These aren't failures of science, they're invitations to dig deeper, to question assumptions we didn't even realize we'd made. The next generation of telescopes and detectors, from the Vera Rubin observatory's all-seeing eye to the gravitational wave hunters like Lisa, won't just test these theories, they'll inevitably uncover anomalies no one predicted. Imagine a future where we finally detect dark matter particles, only to find they're stranger than any model imagined. Or a breakthrough in quantum gravity that reveals galaxies as four-dimensional time crystals, their rhythms echoing from the Big Bang. The most exciting discoveries might be the ones we can't even conceive of yet. Carl Sagan once whispered across the decades, "Somewhere, something incredible is waiting to be known." That's the heartbeat of cosmology, not just the answers we chase, but the awe that propels us forward. Whether you're drawn to the elegant brutality of galactic collisions, the delicate dance of magnetic fields, or the existential thrill of simulation theory, remember, every galaxy out there is a riddle wrapped in starlight, and humanity is just beginning to learn how to read. So tell us which of these cosmic architects sparks your imagination. Is it the invisible hand of dark matter, or the electric fury of plasma, the holographic code, or the ghostly whispers of extra dimensions? Drop your thoughts in the comments, and if you've enjoyed this journey to the edge of the known universe, hit subscribe, because the cosmos has endless mysteries left to explore, and we're just getting started.